Virtualization, this is what has really enabled the cloud movement over the last few years or so. But it's using technologies, configurations to create virtual resources, servers, storage, networks, whatever the case may be. But I've got actual virtual systems doing this as opposed to real physical systems now. That gives me scale. I can distribute things much more rapidly. I have a lot of benefits by going with virtualization. And most of those things that get virtualized look just like their real physical world counterparts. They operate the same, they're fully functional, and it's hard to tell the difference between the two. There are some key differences, but generally speaking, for general computing, you're not going to notice those differences. And virtualization makes a lot of sense. From a security perspective, virtualization is a good thing because it can do several things for you. One, it reduces your attack exposure. You can spin up or spin down virtual machines whenever you need a service. So if you only need a service for a week, you can spin up a virtual machine, let it run, and at the end of that week, shut it down. You don't have a server sitting out there waiting for somebody to attack. Stable and safe configurations. Because virtual machines are just files, you can copy them. You can have multiple copies of it. It's really hard to make a copy of that laptop over there without actually buying another laptop and syncing the configuration. With a virtual machine, it's simple. Copy the files. You've got a backup of your data. You've got a backup of your configuration. You can make snapshots of it, which makes it really easy to switch between the various configurations. And segmentation. This is an interesting one because it allows you to limit communications or access to these machines based on platform, where you're accessing it from, what network you're using, so that if an attack does come in, it can't go anywhere. It's limited to its particular sandbox or its particular segment of the network. The downside to this virtualization is the virtualization manager, the hypervisor. And so this is the single point of control for all the virtualization running on a physical system. The hypervisor controls the virtualization, controls all the virtual machines, the memory management, data storage, everything runs through that hypervisor. The downside here then is if you can compromise the hypervisor, you've got access to everything running behind the scenes there. So every virtual machine that's running on a really powerful server, if I compromise the hypervisor on that server, I now have access to each of the underlying virtual machines. So consider let's just take a typical virtual machine system where you've got a server. It's usually a pretty big server, and you're sharing access to it, like on Amazon EC2 or Rackspace or something like that. If I've got a system that's running some type of hypervisor, say Zen or something like that, and I access and I compromise Zen on that server, I've got access to the 10, 15, 100 virtual machines that are running under that. Now, each virtual machine may not know about its neighbors, but if I compromise the hypervisor, I've got access to all those virtual machines that are under there. And you see this is a pretty big deal. Just probably not more than a month ago, there was a massive patching effort at Rackspace. And I suspect it hit other virtual providers as well, but Rackspace uses Zen. There was a vulnerability in the Zen hypervisor that they were very quick and keen to patch. None of the details of that were released after the fact, but the fact is they ended up running a complete patch upgrade across all of their servers everywhere in the world, and it took them about a week to push it all out. But it's a significant issue when you have a vulnerability in the hypervisor that can be exploited. It allows an attacker to gain control of every virtual machine running on it. Hardware virtualization. So every virtual machine component out there, or every virtual machine platform, has three primary components out there. You've got a host machine. This is the actual physical server that the virtual server or hypervisor is running on. You've got the hypervisor itself. This is the manager. And then you've got guests. These are the virtual machines that are running within that hypervisor. You've probably heard of VMware, VirtualBox, Xen, Fusion's the Apple version of this. There are a lot of different virtualization platforms out there. But I think the three that you see up there, VMware, VirtualBox, and Xen, are probably the largest of them. And they all use the same structure. You've got a host, the physical server. You've got the virtualization piece, the hypervisor. And then within that, you have the machines, the actual guest machines running. An interesting side note to this, or a side concept to this, is virtual desktop infrastructure. This is an interesting case where you can use hardware virtualization to replace the desktop. So rather than the users having a laptop or a full-blown computer sitting on their desk, what they end up doing is running a virtual machine through some simple terminal on their system or sitting on their desk. What this results in is that I don't have all this computing power sitting on the desk that somebody can hack into, that somebody can take advantage of. What I have is for lack of a better term, I have a dumb terminal here that is just showing me the display of a virtual machine running in whatever type of solution I have, or whatever type of VDI solution I have. You see this with Citrix. Citrix has an interesting VDI solution because it allows you to run, each user gets their own desktop, but it's a virtual machine desktop. And at the end of the day, when they log off, that virtual machine gets tossed in the trash. So the next day when they log in, they get a brand new copy of their virtual machine and they go back to work. There are a couple considerations here. One, where's the user keeping their data? If they store it on the desktop, which is a big no-no, they lose it, right? Because that virtual machine's gone when they log off. But if that user gets a piece of malware during the day and they log off, what happens to that malware? It's gone. So the entire attack surface is significantly reduced compared to a typical PC that's up and running 24 hours a day, 7 days a week. So you have the ability using VDI to completely scrub the network clean at the end of the day when people log off and rebuild it. And it all happens in the span of 30 seconds or a minute. It's incredibly powerful from a security perspective. Network virtualization. This is where you're combining networks virtually or logically into one single network entity. You see this with virtual private networks or VPNs. Where multiple home computers might be connecting back into the organizational network through whatever broadband internet connection they have, but allows the network administrators that all they see is one network. All the home user sees is one network, and so you've got this virtualized network running through this. VPNs are used to protect traffic that's going back and forth between the client computer and the home office or the organization networks. Usually, most VPNs assume some type of unsecure or untrusted network that it's transiting, and so solutions like IPsec or SSL VPNs, like OpenVPN. These just assume that whatever network you're on is garbage. I'm going to protect the communication path between us with either IPsec or SSL, and that's how we achieve security of that network. Other VPNs that use MPLS or L2TP, the layer 2 tunneling protocol, do not make that assumption. They make the assumption that everything is trusted, and so it's a different approach to achieving the same type of thing. Memory virtualization, this is where you're combining RAM or random access memory from multiple systems into one single pool. You see this on massive parallel systems, but what ends up happening is this shared pool of memory gets allocated based on the memory manager or whatever is running it, and doled out to various applications or systems as needed. Very similar to virtualization, any type of attacks that compromise the memory manager itself will allow anybody access to that shared memory pool. So again, if I'm on a server and I've got 8 gigs of RAM partitioned into 8 slices, each of those 1 gigabyte slices doesn't know about the other. But if I compromise the memory manager at the top, now I can see down into each of those 1 gig slices and be able to read that virtual memory space. You'll see this done primarily on virtual machine hypervisors, shared hosting platforms where you get your own dedicated server, but it's running on the same physical system. That memory manager is what slices up that memory space and makes it available to everybody else. And then storage virtualization, same kind of concept as memory, but you're taking available storage from multiple systems and combining it into one, or vice versa, where you're taking a large pool and slicing it up into multiple systems. There's local storage virtualization, where you've got multiple hard drives attached to a single host, which get managed as one single logical drive. Most of these are done through virtual file system drivers. And then you have distributed storage systems, where you've got a hard drive over here, a hard drive over here, and they're all coming together as a pool, which then can be accessed as a single drive or something like that. And you see that with distributed file system drivers. A slightly different model is the SAN, or storage area network, and this connects multiple storage devices through some type of high-speed network. SANs provide some type of block-level access to the underlying storage as opposed to file-level access. And it does this for speed and performance reasons. So a SAN will give you very high performance for email servers or database servers or anything that can take advantage of the way that the SAN provisions data through block access. And these various storage virtualization solutions provide some type of security and resilience, because you've got multiple systems all over the place that you can pull data from. A lot of these you can run various levels of RAID through as well. So even if you lose one out of the 3 distributed hard drives, you can still reconstruct the data. And then, of course, you can also do network segmentation with this as well, where you can define that if I've got a storage area network here, only certain people are allowed to access that. And that makes sure that you don't have just cascading compromises of data. The last one we'll talk about here is client-server architecture. And this is very well known, even though you may not know it as client-server architecture. This is the way that the World Wide Web works. Most of the internet works this way, where you've got a single server over here that is serving resources, whatever that might be, web pages, email, memory, storage, whatever the case may be, serving that through the internet to various clients. Could be a mobile client, could be an enterprise client, whatever the case may be. The downside to these types of networks are that they're very susceptible to denial of service attacks, because you've typically got a single server. Let's just oversimplify it. You have a single server here with one entry point. Denial of service means I'm going to target that one entry point and try to saturate it. If I can do that, then everybody this way, the mobile clients, the enterprise clients, nobody's going to be able to access that server. And now we get to cloud computing. So this is the notion that we're combining ideas from memory virtualization, hardware virtualization, network virtualization, client-server applications. We're coming up with a distributed system that is intended to provide some type of service to its clients. It could be data storage, it could be computing resources, anything. There's a lot of different use cases for this that are out there. Just think about things like Box, Dropbox, Picasa, online photo editing. There's a lot of different services that can be provided through a cloud computing construct. There are platform as a service, and this allows you to run applications or stand up entire servers as a platform on demand. So if you look at Google Code, Amazon EC2, Rackspace, all of these companies provide platforms that you can run various things on. And again, you can get this as a bare server. You can get it as an application like a database server or just a web server. It's pretty extensive. Software as a service, these are usually subscription-based applications like Salesforce.com or anything that you might pay, like Pandora, $9.95 a month or something like that for it. But you're getting software or a particular service on a subscription basis. And then infrastructure as a service uses virtualization to create a network, routers, switches, whatever the case may be, that you want to build and you want to hold for a week, 2 weeks. You don't want to go buy all those routers or switches. You can provision it here temporarily on demand using something like GoGrid. So why would you want to do these? Well, there's obvious economies of scale here, right? I can spin up a virtual machine over here, use it for a week, and then shut it off and have no recurring costs after that. It's a lot cheaper than buying a server and letting it sit there unused for 90% of the time. So I can consolidate my applications, my storage, my servers with some type of hosting service and see a lot bigger gains in terms of cost effectiveness and even flexibility. So if I have a web service that I find is really taking off, and I found the billion-dollar unicorn here, and it's really taking off, rather than going and buying hardware to add to that, I can just spin up new copies of it in, say, a Rackspace cloud or an EC2 cloud and add capacity that way. So it gives me the flexibility to grow and shrink as my demand dictates. And I might have the ability to more closely monitor access to this. Maybe not, depends on the service level agreements that I've got in place. But from a security perspective, if I have 100 servers, I may not have the ability to monitor, control, accept input from all of those 100 servers. But I can go get a managed security service provider and have them do it for me. And so I might see a little bit more security gains from that perspective. Some of the cons to this, hosting is done somewhere on the internet. You usually know where your services or servers are physically located, but they could be all over the world. So this enters the world of, I've got data, U.S. citizen data, sitting on a server in, let's pick Germany. What are the implications of that? What privacy regulations and data security regulations do I need to be compliant with? And it gets into gray areas really, really fast. Service provider can access your data and your hardware, whatever you've got with them. They have the ability to access it. So what do you need to do from a data owner perspective? Do you need to encrypt that data? Should you not put that data up there? Now, most service providers are really good about it, and they're not going to go down and access your data. They'd be out of business pretty fast if they did. But just recognize the fact that they do have the ability to do that. So if there's a disgruntled employee at the service provider or an insider, one of your competitors has bought off the guy at the service provider, they've got access to your data and your systems. Do you want to take some type of mitigating action as a result of that? And again, some of these other concerns, users are not always sure where their data is, who's got access to it, and how segregated it is from other data. I know some of the early versions of Zen had vulnerabilities where you could pop from one virtual machine up to the hypervisor, back down into the virtual machine. Oops, that's a big problem. So just recognize the fact that you're on a shared infrastructure here. You're not the only one using that particular server, and so you might run into cases, although exceedingly rare, where that may occur.